So Alfred Wegener published his book in 1915. Geologists didn't buy into it. They saw the evidence, but he could find no mechanism for how the continents were moving. He called it continental drift, and the idea was maybe the continents just plowed through the oceanic crust. It still was not explainable, and the continental crust is rigid, so that would never work. It wasn't until World War II when submarines needed to know the bathymetry of the ocean basins. Bathymetry, bathymetry is like topography, but it's the depth of the water instead of the changes in topography of the land. So echo sounding sonar, there was lots of seafloor mapping at this time. They would send down a sound from a ship to the seafloor. It would bounce back up. They knew the travel rate for the velocity of sound in water, and they could time it using a timer. And all they needed was then they could solve for the depth. So they were able to do that all around the ocean basins and realize that there was a topography, the change in the elevations all throughout the seafloor. So they made these bathymetric maps of the seafloor. Okay, so it looks something like this. They noticed that there were mountain ranges that go throughout the middle of ocean basins. So on this map here, this is the mid-ocean ridge, and this is particularly the mid-Atlantic ridge. You are going to be creating a cross-section that looks much like the gray one here on the bottom in the lab exercise GeoMap app. Okay, and you're going to label it much like this. The mid-ocean ridge is kind of wide. It's a topographical high, and they detected that by doing these sonar studies. They also found really deep trenches around the ocean basins and submarine volcanoes and fracture zones. All of that led to plate tectonics. Once they realized, geologists realized that the sea floor had a topography, they could start to explain different phenomenon and start to explain how the plates move. So here is an image of, this is a cross section across the South Pacific from the Peru-Chile Trench. So this is the Peru-Chile Trench here. This is the Tonga Trench on the other side. And there's another mid-ocean ridge in between, in the middle of the South Pacific. Realizing that there were these deep trenches on the edges of continents was really important. Over here on the right is the trench that is south of Japan, so Marianas Trench. Okay, so deep trenches, mid-ocean ridges, and another thing was these fracture zones. So the way the ridges are drawn on the seafloor, notice they kind of have a stair step to them. That is because it's not just a straight line. They are there are fractures that are across the mid-ocean ridge. So the trace of it looks something like this, but it's cut by these fractures along the way. Okay. Another discovery, again, we're just building up the evidence for plate tectonics, was that the thickness of sediment changes from the mid-ocean ridge axis out to the edges of our ocean basins. It's very thin at the ridge and thick at the edges of the basins near the continents. So how could that be? What could explain that there's thin sediment at the ridge and thick as it goes across the ocean basins? Think about that for a second. It turns out that at the mid-ocean ridge axis, new oceanic crust is forming. So it's born today. There's no sediment on top of it. Over time, that new crust moves away from the ridge and more new crust, like a volcano, comes up into that space, and it continues to move apart, continually bringing in magma and new oceanic crust and spreading apart. So the further away from the mid-ocean ridge, the older the oceanic crust is, the more time there would be for those sediments to fall down and accumulate on the oceanic crust. It's just older crust has more sediment on it because the time is there for it to get thicker. They also observed heat flow, so there's a high heat flow at the ridge. It's essentially a ridge of volcanoes, and there's less heat flow in the cooling crust away from the ridge. The rocks coming out of the mid-ocean ridge are basalts and gabbros. Basalts are at the surface and gabbros are deeper down within the crust. That's a fine-grained, basalt is a fine-grained, meaning really small crystals, igneous rock cooled from lava, and it has lots of iron and magnesium in it. Remember, the mantle has lots of iron and magnesium, and that material is coming up and forming the rocks of the oceanic crust. There's no granites there, there's no metamorphic rocks, it's just all basalt. If you map out earthquakes on a map of the earth here, that's not all of the earth, but yeah, map out earthquakes, the map shows kind of like a dot to dot. If you were to connect those dots through the mid-Atlantic, you would be basically tracing the mid-ocean ridge. The same thing around Africa and through Indonesia and into the Pacific. So the earthquakes are in these linear belts, and earthquakes form where the Earth's crust is moving and it's breaking. And so those places are the active plate boundaries. So we're starting to get an idea that these continents, like let's look at Africa, it has that yellowish color to show the land part of Africa. But if you go out into the sea, that's the whole African plate. So this blue here of the ocean is attached to this plate, and all of this I'm circling here, well, most of it, is the African plate that has oceanic and continental crust part of it. Okay. We're going to talk about plate tectonics for a while, so we'll just keep going. Here is the sea floor, then across the Atlantic Ocean with the mid-ocean ridge in the middle, an abyssal plain, that's just a flat, deep area of the ocean, and then come up to the continental shelf, the slope, the rise, the slope, and the shelf here on either side, symmetrical. So Harry Hess in the 1950s, he was in the Navy and a geologist, so perfect combination. He was out on these ships and he was out there with the sonar getting the bathymetry of the oceans. When he would see a feature, he would try to follow that feature as far as he could, eventually making maps of the bathymetry of the seafloor. He realized that sediment thickness, he realized there was a difference between the rocks of the ocean, these basalts, and the rocks of the continents. They were able to map that heat flow, look at the linear belts of earthquakes, and trace those ridge axes. So he was able to talk about the ridge as a place where new oceanic crust was forming. There's hardly any sediment there. It's brand new. It's deep in the ocean. There were volcanoes. And then on the other end of that, there was this trench. And his hypothesis that turned out to be true was that the oceanic crust was getting recycled back into the earth at those trenches. So here's on the cartoon, it shows the oceanic plate descending into the mantle. So that's recycling that old oceanic crust. Here is a trench. When that crust goes down into the mantle, it's going to melt. All these little stars are earthquakes. it's going to melt. That magma rises up to become volcanoes. This one is shown on a continent. And then over here on the other side of the continent, we have another ocean basin. And here is a mid-ocean ridge with volcanics coming up again. So we have a place at the ridge, whoa, my hair, where the magma is coming up and new crust is being created. And then somewhere in the ocean basin, another ocean basin, old oceanic crust is going down and being recycled back into the mantle. Ta-da! Plate tectonics. So Alfred Wegener with the idea in the early 1900s, the late 50s, Harry Hess coming up with this mechanism and the seafloor. Then it was not till the early 70s when it started being in textbooks that plate tectonics was a thing. So continental drift turned into seafloor spreading, turned into pretty much plate tectonics. Seafloor spreading just means at those ridges you have the new magma coming up and it's a divergent plate boundary, but I'm getting ahead of the story. At that divergent plate boundary, the plates are diverging and coming apart and new magma is coming up. So that provided this mechanism for continental drift. What was allowing those continents to move around? Upwelling mantle erupts at the mid-ocean ridge. New crust moves away from the ridges, gathering that sediment. As it gets older, thicker sediment gets on top of it. At the trenches, those deep parts of the ocean, then that old oceanic crust, it's old, it's cold, it's dense, gets recycled back into the mantle. Okay. Another part of the story are these magnetic reversals. So we kind of had an idea that that's what was happening, but now we needed more evidence. And magnetic reversals provided that evidence. We talked before about the magnetic field, that it's a dipolar. It's like having a magnet in the middle of the earth with a north end and a southern end. Well, every now and then it flips. And when it flips, you have an anomaly that's different than the way it is now, and it flips, and when it does, there's a geologic record for that, and the record is in minerals that have iron in them. That iron is going to literally grow as it crystallizes, oriented in a way to mark where the North Pole is. The iron crystals do. So if you flip the north arrow for the Earth, flip the magnetic field, then those crystals flip. And we can actually get a record of that by looking at the seafloor, these magnetic reversals. Here's an example of magnetic reversals just in a really big volcano. So this is a volcano, and this is the neck here where the magma is coming up from the magma chambers, not on here, but it'd be down below. Magma is coming up and erupting, so every time it erupts, there's a layer of igneous rock being deposited. And over here on the right, we can see positive and negative flips, each of those, the tip moving back and forth of the reversals of the Earth's magnetic field. Okay, so they took ships across the seafloor, and they would, on a long line, have what's called a magnetometer. And the magnetometer is measuring the strength of the magnetism coming from the rocks. So it would be strong when there was a positive anomaly, when it's normal, like normal times. Then it would be weaker when we had a negative anomaly at times when the magnetic field had flipped. So positive and negative, stronger and weaker with magnetic intensity. And it was recorded on the seafloor. Perfect evidence for that seafloor spreading. Okay. They formed a pattern, right? So if at the ridge you are forming new basalt and it's moving away from the ridge, then this basalt would have the same signature because it formed at the ridge at the same time. So here is a ridge that is actually a ridge of this microplate. This is the Juan de Fuca plate that is subducting or going down in a trench off the coast of the Pacific Northwest of the United States. So this red line marks the ridge, and on either side of it, it's not perfect, right? But the data shows these stripes, these positive and negative anomalies symmetrically across that ridge. Okay. So we're able to date those anomalies. Here's the age on this axis. It's age in millions of years. We can date the reversals and see the positive and negatives and have a record of it. Okay, so here is what some real data looks like. Let me turn my face off. This is the mid-Atlantic ridge axis, and these colors represent intensities of magnetism, and again, symmetrical across the ridge. On the left, here's zooming in of the mid-Atlantic ridge just down ridge from Iceland. Iceland is a country that sits actually right on top of the mid-Atlantic ridge. And here's the data zoomed in just south of Iceland, showing that ridge axis and the symmetry of the flips in the Earth's magnetic field. Really showing, indeed, that the rocks form at the ridge and move away from the ridge symmetrically. We can mark that time with these positive and negative anomalies. Okay, here is what it looks like again. We have furthered the use of these magnetic anomalies by measuring the distance that the stripes move away from the ridge. If you know the distance and you know the age of the rocks, you can start to calculate the rate of plate motion. So for like the Mid-Atlantic Ridge, it's 2 centimeters per year. The East Pacific Rise is a spreading center in the East Pacific, and it spreads way faster, something like 10 centimeters per year. The average of plate movement is more like 3 to 5 centimeters per year. So in time 1, you have that gray rock forming at the ridge. Time 2, times 3. Measure that distance. The rate is distance over time. Here, centimeters is the distance in per year. We can figure that out, the rate of plate motion. Okay, here is a record across a spreading center. The width of the stripes matter. So during times when the stripes are pretty wide, it shows that the plates were moving faster than when the stripes are kind of thin. So we can look at the width of stripes, we can look at the where they are centered across the ridge. So they're used in a lot of different ways. Okay, that's the end.